Hello everyone, myself Sachin Gaware from RBNB College, Shrampur. In today's lecture, we continue our chapter from 12th Science paper first, that is linear programming. In this chapter, we start today exercise 7.4. In this exercise 7.4, we have to solve the given LPP by using the graphical method. Now, first we take the first problem, that is maximize or max z equals to 11x plus 8y. This is the objective function. Subject to x is less than or equals to 4, y is less than or equals to 6, x plus y is less than or equals to 6. And the non-negative constraints, that is x is greater than or equals to 0 and y is greater than or equals to 0. Now, to solve this LPP by using graphical method, first we find the feasible region. First we find the feasible region for the given constraints, and to find the feasible region we have to plot the constraints on graph. So to find the graph, first take the line, then x equals to 0, y equals to 0. Now the first constraint is x is less than or equals to 4, so the corresponding line is x equals to 4. Next one is x is less than or equals to 6, so y is less than or equals to 6, so the next line is y equals to 6. And the third line is x plus y equals to 6, because the constraint is x plus y is less than or equals to 6. Now these are the standard lines or parallel to x-axis and parallel to y-axis lines, so we can draw it directly. Now for the third line, first we put x equals to 0. Whenever we put x equals to 0 in this equation, it gives y equals to 6. So the first point is 0, 6. Similarly, if we put y equals to 0, we get x equals to 6, so that is the second point is 6, 0. So we get the 2 points 0, 6 and 6, 0 for the line x plus y equals to 6. Now we plot a graph for this one. So to plot the graph, take x and y axis. This is x-axis, y-axis, and taking appropriate scales. Suppose this is 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. Again here it is 1, 2, 3, 4, 5 and 6. Taking 1 centimeter as a 1 unit. Now the first line is x equals to 4, that is the line passing through x equals to 4. Here it is the x equals to 4, this is the origin. So this is the first line, that is x equals to 4. This is the first line, that is x equals to 4. Now the next line is x equals to, y equals to 6. So this is the second line, y equals to 6. This is the second line, which is y equals to 6. And for the third line, we have to join the 2 points 0, 6 and 6, 0. Now this is the 0, 6 and this is the 6, 0. Now by joining these 2 points by a line, this is our third line, that is x plus y equals to 6. Now to find the feasible region, that is the region which satisfies all these constraints, we consider the inequalities. Now for the first line, the inequality is of the type less than or equals to. So we have to consider the region towards the origin for the first line. So this is the region towards the origin for the first line. Now for the second line, it is also less than or equals to, so we have to consider now the region below the line. So the region below the line is this region, whole the region. And for the third line, now again the third inequality is of the less than or equals to, that is again below the line towards the origin, or we can say that it is the from origin side. So for the origin side, this is the region. So if we take the common region which is satisfied by all these three constraints, this will be the feasible region. This will be the feasible region. So the feasible region, that is the region or set of decision variables which satisfies all the constraint, is this one. So we denote it as by feasible region or FR. Now giving the points for the corners of this feasible region. So let this is the O, this point is A, this is B, and suppose this is C. And therefore we can write here the feasible region here. The feasible region is bounded because it is the polygon. Because it is the polygon, so it is the bounded. So it is the bounded region which is O, A, B, C, O. O, A, B, C and O. This is the bounded region. In which write the coordinates which are known directly. Because the O is 0, 0. Then A, this A is a point on x-axis, that is 4, 0. And C is 0, 6. C is 0, 6. Now the remaining point B is the intersection of the third and first line. The point B is the intersection of first and third line. So here we write, and point B or corner B is intersection of first, that is the first line is x equals to 4, and third line, and the equation of third line is x plus y equals to 6. The point B is the intersection of x equals to 4 and x plus y equals to 6. To find the coordinates of this point B, we solve these two linear equations, these two linear simultaneous equations. So putting x equals to 4 in second equation, we get y equals to 2. So here we write, by solving these two equations, by solving these equations, we get the coordinates of B, that is x equals to 4, and by putting this x equals to 4 in this equation, we get y equals to 2. So we get coordinates of B as 4, 2. Now for this feasible region, now we get all the corner points, coordinates of all the corner points of the feasible region. Now at these corner points, we find the value of objective function, that is z. We have to find the value of objective function z. So here we consider that z equals to, the value of z is 11x plus 8y. Now next, find the value of z at each corner of the feasible region. Now starting from origin, z at O, this can be written as z at 0, 0. That is the putting the values of x at 0 and y at 0, we get 11 into 0 plus 8 into 0, so we get totally 0. Now next is z at A, and the coordinates of A are 40, that is, it is z at 40. So it gives 11 into 4 plus 8 into 0, which gives 44. 11 into 4, 44 plus 0, that is 44. Now next is z at b, and the coordinates of b are 4, 2. The coordinates of b are 4, 2. So it gives 11 into 4 plus 8 into 2, which gives 44 plus 16, that is 60. And last is z at c, that is the coordinates of c are 0, 6. So z at 0, 6. So this can be written as 11 into 0 plus 8 into 6, that is 0 plus 48 equals to 48. Now the objective function is of the type maximize. So we have to find the maximum value from this one. Now, if we observe here, the maximum value of z is 60. Maximum value of z is 60, which is at a point B, 4, 2. And so, the solution of this LPP becomes, therefore, z max. Or you can write maximum value of z max equals to 60 at B 4, 2, that is when x equals to 4 and y equals to 2. This is the solution for the given LPP. Now again, see here, to find the solution of a given LPP, first we find the feasible region. First we find the feasible region for the constraints. And in LPP, always there are the non-negative constraints, that is x is greater than or equals to 0 and y is greater than or equals to 0. That means it shows the first quadrant only. It shows the first quadrant only. Now after finding the feasible region, again remember that feasible region means the set of all points which satisfies the condition or constraints, all the constraints. After finding this feasible region, we find or we write the corner points, coordinates of the corner points of an feasible region. In some cases, like here, the point B is the point which is the intersection of two lines. And so, to find the coordinates of this point, which is the intersection of two lines, we solve that two lines, equations of that two lines, and we find the coordinates like this B here. Solving the two equations, we get B equals to 4 and 4, 2. B is 4, 2. Then take a Z, which is objective function. Find the value of Z at each corner point of a feasible region. Remember one thing again, we have to find the value of Z at the end points, only the end points of a feasible region only. See here, we not find the value of Z at this point. This is the corner point. But it is not a corner point of a feasible region. This point, also this is the point of intersection. But here we not solve or we cannot find the value of Z. It is unnecessarily. We have to find the value of Z at the corner points of feasible region only. After finding the values of Z at each corner of the feasible region, then observe the objective function. Here the function is maximum type, so we select the maximum value of a Z and corresponding point. If the problem is of the type of minimization or minimum, then we find the minimum value. Only difference is selecting minimum and maximum value with respect to the type of the objective function, which is either maximize or minimize. Now we see the next example. Now see the next example. Max z equals to 4x plus 6y, subject to the constraint, that is the conditions. 3x plus 2y is less than or equals to 12, and the second condition is x plus y is greater than or equals to 4. And obviously the non-negative constraints, that is x is greater than or equals to 0 and y is greater than or equals to 0. Now to find, first we find the feasible region. Now to find the feasible region, we plot a graph. So here it is line, we make a table line, x equals to 0, y equals to 0. Now taking first constant as a line, that is 3x plus 2y equals to 12, and the second one is x plus y equals to 4. X plus y equals to 4. Now when we put x equals to 0 in this equation, it gives 2y equals to 12. 2y equals to 12 means y equals to 6. So we get the first point 0, 6. Similarly, if we take y equals to 0, we put y equals to 0, we get a 3x equals to 12, which gives x equals to 4. So the second point is 4, 0. Now similarly for the second line, if we put x equals to 0, we get y equals to 4. Similarly, if we put y equals to 0, we get x equals to 4. Now make a graph. In this graph, this is the y-axis, x-axis, take the unit, 1 centimeter equals to 1, that is 1, 2, 3, 4, 5 and 6. Here 1, 2, 3, 4, 5 and 6. Now the first point is 0, 6. Now 0, 6 is here. And the second point is 4, 0. Again this 4, 0. Now by joining these 2 points by line, this is the first line, this is the first line. Now for the second line, 0, 4 and 4, 0. This is 0, 4 and this is 4, 0. Again joining these 2 points, we get the second line. We get the second line. Now observe here, the first constraint is less than or equals to type. So we have to consider region which is towards the origin, or we say that origin site of the first line, that is this region. Origin site of the first line, this region. And second constraint is of the type greater than or equals to, that is the opposite or above the line or away from the origin. So this region is for the second line. And so the combined region which satisfies both the constraint is, this is the triangle. So we get, this is the feasible region. This is the feasible region of this LPP. A feasible region, that is a region which satisfies all the constraints. Now we give the names, like this is A, this point is B, and this is the C. The coordinates of A are 0, 6. The point B, this is the point B, B is 0, 4. And this is the point C, that is 4, 0. These are all the 3 corner points of a feasible region. Now we find the values of an objective function z equals to, let z equals to 4x plus 6y at these 3 points. At these 3 points. So z at A, that is z at 0, 6. Z at 0, 6. Putting the value of x equals to 0 and y equals to 6, we get 4 into 0 plus 6 into 6, which gives 36. Which gives 36. Similarly, z at B, the coordinates of a point B are 0, 4 here. Now, so z at 0, 4. Z at 0, 4. So, putting the value of x as a 0 and y as a 4, we get 24. And next one is z at C, that is z at 4, 0. So, it gives 4 into 4 plus 6 into 0, that is 16. Now here we write here the feasible region. The feasible region is bounded region. Feasible region is bounded region A, B, C, A. Now the objective function is of the type maximization. Now the maximum value, since the maximum value of z is 36, the maximum value of z is 36, which is at a point 0, 6. So we write the solution, that is, therefore max z is equals to 36 at point A 0, 6, that is when x equals to 0 and y equals to 6. This is the solution of a given LPP. In next lecture, we solve more problems on this LPP. Thank you.